Okay, students, today we will discuss the black box analysis of the op-amp in feedback configuration. Okay, firstly, we will represent the block diagram of the op-amp in feedback configuration, or you can say that it will be the closed loop amplifier. Closed loop because there is a closed circuit between output to input. Okay, as in the open loop configuration, there is no any communication between the input and output, but in closed loop amplifier there is a connection between the output to input through a feedback circuit. Okay, so in closed loop amplifier there are two parts, an op amp and a feedback circuit. There are four ways to connect, or four way configurations are there. Firstly, the voltage series feedback. Firstly, voltage series feedback. Then second, voltage shunt feedback. Then current series feedback, current shunt feedback. Okay. So first, voltage series feedback. This is the voltage series feedback. Okay, this type of connections will be there as by the block diagram representation. This block is for the op amp and this block is for the feedback circuit may be any type of circuit may be there, but we are representing all feedback circuit by this block diagram. Okay, now in input side, input voltage source is applied as by the symbol, some AC voltage source is applied. So input connections are shown by these arrows. Okay, on the output side, output voltage that will be represented across some load resistor, and this voltage, output voltage, is applied to the input side by some feedback circuit. So here shown V naught is applied in the feedback circuit. Okay, and by feedback circuit some partial part of this output voltage as Vf will be applied to the input side. This is the voltage series feedback. So as by connection show, or we can remember by this connection as you can say here plus minus. Okay, as symbols for the output voltage. So plus side is connected to the minus side of this input voltage, and this minus side is connected to the plus side of this input voltage. Okay, now we can remember by this, if there is a voltage series feedback, then it means plus side of this is connected to the negative side of this input voltage, and negative side of this is connected to the plus side of this input voltage. So this is the voltage series feedback, and second is the voltage shunt feedback. Voltage shunt feedback. Okay, so about same structure is there with the minor differences, as one block is for op amp, one block is for feedback circuit. Input voltage, input voltage input voltage source is connected in this way. Okay, plus side is this, minus side is this, right? uh, Output voltage is measured across this load resistor. Okay, and that is connected through this feedback circuit, right? Now this feedback circuit, as you can see the connections, as plus side of this output voltage is connected to the plus side of this input voltage, minus side of this output voltage is connected to the minus side of this input voltage. So this is the shunt connection, or you can see the parallel connection of the input voltage. Parallel connection of the input voltage. Okay, so and the next block diagram representation is for the current series feedback. Current series feedback. As you can see, there are two blocks. There are two blocks for current series feedback. As V input is applied, okay, and current through the load resistor is applied through this feedback circuit, and feedback circuit connections you can see in this current series feedback. Okay, because current connection as you can see the difference between this voltage series feedback symbols and current series feedback symbol. Current series. Okay, please remember these block diagram representation. Okay, so then there is a block diagram representation of current current shunt shunt feedback. Current shunt feedback. Okay, we will draw the circuit in the same way with minor differences. Op-amp. Okay, block diagram for feedback circuit. Okay, then input voltage source is connected. Okay, V input plus minus, then output voltage. Okay, here we will consider the output current through this load resistor RL, and value of current will be IL passing through this load resistor, and some partial part of this load current will be applied to the input side of this op-amp. Okay, so connections may be represented by these arrows. Okay, firstly signal will go in this direction, then signal will go in this direction, but partial part of this load current will be connected back to the input side of this op-amp. Okay, so because this is a shunt connection, so just like connections will be same as in the voltage shunt feedback. This. Okay, so input current I input. Okay, after this connection base current. Okay, and load current is flowing IL through this ohmic contact. Okay, so these are the four configurations, four connections of a feedback circuit. Okay, now we will discuss the very important connections, very important configuration of feedback or closed loop amplifier as a voltage series voltage series feedback amplifier. Voltage series feedback amplifier. Okay, here we draw a typical circuit of feedback amplifier, closed loop amplifier, op amp symbol, non-inverting and inverting terminal, voltage sources connected, V input, then output voltage we will measure across a load resistor RL, and second terminal of this load resistor is connected to earth, and power supply negative terminal will be connected to this earth. Okay, now we will show the feedback circuit as in this way. This is the feedback resistor RF. Feedback is connected through this feedback resistor RF, and through this resistor R1. Okay, and feedback connection is shown by this way. Okay, so here on the non-inverting terminal V1 is applied, and inverting terminal V2 is applied, and what will be the actual voltage applied? Difference voltage VID. Okay, VID is equal to V1 minus V2, and open loop gain or large signal gain A will be shown here. Okay, or we also can show the power supply pins of this op-amp IC as a plus VCC and minus VEE. Okay, these are the power supply connections of this op-amp IC, right? Now partial part of output voltage which is measured across this load resistor. Okay, plus minus, right? Now partial part of this output voltage is applied to the input side in the voltage series feedback configuration feedback amplifier. Now the part of voltage of this output voltage as Vf, that is drop across this R1 is applied to the input side. Okay, Vf, right? Now what it means? This this part is the feedback circuit. Okay, now you can see the difference voltage is applied to the input terminals of this op amp. It means you can write VID is equal to V1 minus V2. Okay, now on the V1, V1, what is the voltage applied as a V input? V1 is equal to V input. And on the V2, what is the voltage applied? On the V2, voltage applied is a, on V2, voltage applied is a Vf, because this feedback voltage part is applied on this inverting terminal. Okay, and on non-inverting terminal there is the voltage applied as V input, right? So we can write as Vid is equal to V input minus Vf. Okay, as you can see here as a V input, or you can say on the input side, on this loop, in this loop, if you analyze this loop, there are three voltage drops as Vid, V input, and this Vf. If you do the analysis like this, then you can say this. Okay, in closed loop, if you do the analysis, then Vid is equal to V input minus Vf. It means the output voltage that is applied to this input voltage side, output voltage that is applied to this input voltage side, because the symbol against this Vf voltage is minus. Okay, so it means the feedback voltage is applied in the phase difference of 180 degree. It means this voltage Vf is 180 degree out of phase of this V input. So by this equation we can say this is the negative feedback circuit. This difference voltage, because input voltage minus feedback voltage, or in other words, the feedback voltage always opposes the input voltage. Okay, or you can say it is a out of phase by 180 degree with respect to the input voltage. Hence feedback is said to be feedback is negative feedback. Negative feedback. Okay, feedback is a negative feedback amplifier, right? Now we will discuss some more closed loop features, or closed loop properties. So firstly, the closed loop voltage gain. Closed loop voltage gain. So what will be the closed loop voltage gain? As AF will be equal to V naught by V input. V naught by V input. Okay, this is the closed loop voltage gain. Okay, as if you remember that open loop voltage gain, what will be the value? A is equal to V naught by Vid. Okay, V naught by Vid. Now, what will be the gain of feedback circuit? Gain of feedback circuit. What will be the gain of feedback circuit? Because what will be the input of this feedback circuit? That is V naught. And what will be the out of this feedback circuit? That is Vf. It means gain will be Vf by V naught. So it means you can represent this gain by B. Okay, just name that. B is equal to Vf by V naught. Okay, so we just write here AF closed loop voltage gain is equal to V naught by V input. Okay, but we know that V naught is equal to A V1 minus V2. Okay, this is a very typical equation of our op-amp. Okay, A into V1 minus V2. Okay, so now what will be the V1? V1 is equal to V input, as in this case, because on V1 side on non-inverting terminal there what is the voltage applied? V input. V1 is equal to V input, and V2 is equal to Vf is equal to R1 by R1 plus Rf into V naught. Okay, by this circuit. On V2 side on inverting terminal, what is the voltage applied? As by the potential divider circuit. Okay, R1 by R1 plus Rf into V naught, because V naught is applied. Okay, V naught is applied in this feedback as an input. Okay, so we write that V2 is equal to Vf, and what is the Vf? Vf is equal to R1 by R1 plus Rf into V naught. Okay, here we are considering that since our input is very much greater than R1. Okay, we are considering this because input resistance of op-amp is very much greater, very much high as compared to any resistance that is connected in the input circuit. So our input is very much greater than R1. Okay, so we just apply all these values to the equation. V naught is equal to A V1 minus V2. So is equal to A V1. What is the value of V1? It means V input, minus V2. It means R1 by R1 plus Rf into V naught. Okay, so now we just take the common value of V naught. Okay, we just rearrange these values at V naught is equal to A into V input minus R1 by R1 plus Rf into A into V naught. Okay, so we just combine these two factors, as we want to take the common V input as in this way, 1 plus R1 by R1 plus Rf into A. Okay, is equal to A V input. Okay, now take the LCM. So it means V naught R1 plus RF plus R1, okay, R1 into A, right, by R1 plus RF, okay, is equal to A into V input, right. So it means V naught is equal to R1 plus RF, R1 plus RF into A into V input by R1 plus RF plus A into R1. Okay. Now we can write as we just take this factor in the denominator of this as we make the ratio of or you can say that we divide V input on both sides. Okay, so we can write as V naught by V input is equal to A R1 plus RF by R1 plus RF plus A dot R1. Okay, so you can write this factor as AF is equal to this. V naught by V input is equal to this. Okay, so it means AF is a closed loop voltage gain V naught by V input. Okay, generally open loop gain A is very much large, is very much large. Okay, this gain is very much large. So you can see, if you compare this factor with this, it means AR1 very much greater than R1 plus RF. Okay, so we can write as AF is equal to V naught by V input is equal to A R1 plus RF by A R1. Okay, so you can cancel out this A, right? So we can write this 1 plus RF by R1. Okay, for ideal case, because here we consider that input resistance is very much high as compared to any resistance that is connected in the input side. Okay, this is the closed loop gain. AF is equal to 1 plus RF by R1. Okay, this will be the closed loop voltage gain, right? So firstly we define the open loop gain. Okay, then we define this closed loop gain. Okay, so also in feedback circuit we defined the factor as beta, that is equal to Vf by V naught, because what it is showing, that partial part of output voltage is applied to the input side, Vf. Okay, so this Vf by R1, and you can write this Vf as the R1 by R1 plus Rf dot V naught. This Vf is equal to this factor, but by V naught. So we can cancel this V naught. So we can write this Beta B, okay, is equal to R1 by R1 plus Rf. Okay, so if you compare AF is equal to this, and beta is B is equal to this, then you can just conclude that AF is equal to 1 by B. AF is equal to 1 by B. Okay, and if you say uh, if you divide this numerator and denominator, if you divide this numerator and denominator, we just do this analysis. Some more analysis is there, some more conclusions are to find out. If you divide this numerator and denominator by R1 plus Rf, if you divide that, AF is equal to A, because we are dividing this numerator by R1 plus Rf by this factor. So by this factor, 1 plus A R1 by R1 plus Rf. Okay, it means A by 1 plus AB. So AF is equal to this. This what I want to show you. AF is equal to, because this is the closed loop voltage gain and this is the open loop voltage gain, and this is the feedback circuit gain. Closed loop voltage gain, open loop voltage gain, gain of the feedback circuit. So this is a relation between these three. Okay students, thank you so much.